Good day, and thank you for joining me in this session where we'll discuss how Ansys HFSS can be used to design, test, and validate advanced driver assistance systems. Today, the spotlight will be on automotive radar. The automotive industry has seen a recent surge in the development and deployment of advanced driver assistance systems. Such trends have caused ADAS to be one of the fastest growing markets in the technology sector. The automotive industry is seeing a shift in ADAS implementation and adoption from low-volume, high-end vehicles to high-volume, low-end vehicles. Therefore, experts have projected that by 2021, original equipment manufacturers, or OEMs, who will be spending over 37 billion on ADAS and safety-related electronics. With fully autonomous vehicles being the ultimate manifestation of ADAS, much of the growth in the ADAS market has been attributed to OEMs racing to deploy the first commercially available, fully autonomous vehicle. The global autonomous vehicle market was valued at 54.23 billion in 2019. This number is expected to rise to 560 billion by 2026. Therefore, there's an enormous financial incentive to develop advanced driver assistance systems that will serve as the backbone of fully autonomous vehicles. An even more compelling reason for developing and deploying advanced driver assistance systems is to equip vehicles with systems that make our roads safer and subsequently preserve human life. According to the NHTSA, 36,560 people lost their lives in road traffic accidents in 2018 alone. For context, this is equal to almost the capacity of Fenway Park in Boston. With road traffic accidents being the leading cause of death globally for young people aged between 5 and 29, one wonders if such loss of life could be avoided if cars could see and talk to other cars, and possibly even talk to the road that they're driving on. That is, can technology such as vehicle to everything, that is V2X, and radar help to prevent accidents and save lives? In today's presentation, we will be showing how Ansys HFSS can be used in the design and optimization of automotive radar antennas. Using HFSS, we will demonstrate how we can evaluate the impact of packaging and electrically large platforms on the radiation performance of radar antennas. We will also show how full-scale dynamic traffic scenes can be created to obtain full physics synthetic radar returns for range, Doppler, and angle of arrival processing. Now, using this workflow as a foundation, we will show how HFSS can be used for Micro-Doppler and direction of arrival analysis using MIMO antennas in automotive radar. We will demonstrate how using simulation, we can evaluate the response of automotive radar systems in corner cases. Finally, we will show how the above-mentioned workflow can also be adopted to test vehicle-to-everything or V2X communication links. As previously mentioned, the ADAS development workflow in HFSS can be broken down into three key stages. In the first stage, HFSS is used to design and optimize electromagnetic structures on a component level. This could be antenna design for automotive radar, smart remote keyless entry systems, V2X applications, among others. In the second stage, HFSS is used to evaluate how the package and platform where the component is mounted on can affect or modify its performance. In relation to radar, for example, this involves evaluating the impact of a vehicle fascia or bumper on the radiation characteristics of the antenna. Finally, HFSS is used to evaluate the performance of these packaged and mounted components in driving scenarios. For example, this could involve obtaining synthetic radar returns or simulating the antenna-to-antenna coupling in V2X communication links. The workflow described here rapidly scales up in electrical size as we move from one stage to another. So how does HFSS maintain accuracy and efficiency in such a workflow? On a component level, HFSS FEM is the unrivaled gold standard in accuracy for simulating electromagnetic problems with high geometry or material complexity. HFSS IE is a fast method of moment solver technology that allows for the efficient full-wave simulation of larger problems. For even larger problems, we can use HFSS SBR+, an asymptotic, full physics-based shooting and bouncing ray solver. Using hybrid simulations, all of these solver technologies can be brought together to solve both electrically large and complex problems. Now let's take a look at how these solvers in HFSS can be used for automotive radar. Now, when it comes to automotive radar, we know that automotive radar is an integral part of advanced driver assistance systems. The key areas of interest in automotive radar design are antenna element design and optimization, investigating placement effects, full physics simulations of radar scenes, and investigation of radar corner cases. Now, Ansys can simulate all these key areas of interest in automotive radar. The first stage would be antenna design. Here we show how HFSS FEM can be used to design, in this case, a single 5-element tapered series-fed microstrip antenna array. Using HFSS, we can determine the dimensions that we need in order for us to get resonance at the right frequency, and we can also determine the resulting radiation pattern. To simulate even larger arrays, we can leverage the HFSS FEM 3D component domain decomposition method, DDM, for arrays. Here, we use a single element to create a 3D component. This 3D component can then be stacked along with other 3D components and used inside a much larger array. In this case, an 8 by 12 element array is being simulated using the HFSS 3D component domain decomposition technology. This array is 24 lambda by 25 lambda. What we see is that this technology allows us to achieve fast, accurate, and efficient full-wave solutions for large arrays. Here are some of the results that we can obtain by simply using this 3D component DDM technology. For this antenna, which has a total of 20 excitations, the simulation took around an hour and 5 minutes with only 16 cores. And we must note that this is for all 20 excitations being solved simultaneously. Having designed and optimized the antenna, the next step is integrating the antenna on a platform. For this stage, we begin with the vehicle model where the antenna will be placed. Now, assuming that this antenna is going to be placed on the fascia behind the emblem, we can then take this particular component and simulate this inside HFSS FEM. In this situation, we have the radar sensor mounted inside a housing on a mounting bracket behind the emblem, which serves as the dielectric radome. The antenna housing packaging and the radome on the vehicle fascia can change the radiation characteristics of this antenna. And using HFSS FEM, we can simulate and observe how the housing and the fascia can lead to drift in the resonant frequency of the antenna, as shown here by the S11 plots that were obtained using HFSS FEM. Another study that we can conduct is to look at how placing this antenna on a platform can cause changes in the antenna isolation that we would have if the antenna is in free space. For example, when in the first case in free space, when one antenna is excited, very little power is coupled onto the other receivers. However, placing the antenna inside the housing and placing a radome on top creates a resonant cavity that leads to poor isolation between the antennas inside the radar sensor, and this can degrade radar sensor performance. Another issue that we can investigate using HFSS FEM is the radiation pattern and antenna blindness that can come around as a result of the antenna placement effects. We see how the fascia reduces the field of view of the sensor. A gain reduction of over 14 dB is observed in this case. This can manifest itself in that during normal operation, the radar sensor can become blind at certain angles. In this case, it will be around -75 or 75 degrees. So in summary, we were discussing how HFSS FEM can be used to design an antenna and evaluate its performance in free space. We can also take that antenna, mount it on a platform, and place it behind a radome and conduct a full wave solution using HFSS FEM. In order to solve the even larger problem of the antenna being mounted on a full vehicle, we can use hybrid techniques such as HFSS FEM and SBR Plus being used in conjunction, or HFSS FEM and HFSS IE being used at the same time. To look at the impact of how the fascia study can affect the performance of an antenna, we're showing here two range Doppler maps that are being seen from the same for the same scene, one using an antenna in free space and the other using an antenna behind the fascia. We have two vehicles here at around 175 meters that can be clearly seen when using the antenna in free space. However, when we place the antenna behind the fascia, we start to see that these targets are no longer as visible. So the free space antenna can detect two vehicles at a range of 170 meters, while the one with the antenna behind the fascia cannot. And this could mean a possible reduction in the detection range of the sensor. Having determined this, we can go to the next level of where we want to test the radar sensor in a full-scale traffic scene. In order to do this, we use the HFSS SBR Plus technology. Now, HFSS SBR Plus is an asymptotic full physics-based shooting and bouncing ray solver with complementary capabilities to HFSS FEM. This solver can efficiently solve electrically large problems. HFSS SBR Plus uses geometrical optics to launch rays from a radiation source. These launched GO rays are vector field weighted by the radiation pattern of the current distribution of the source antenna. HFSS SBR Plus then uses physical optics to paint currents wherever GO rays hit a geometry. Physical theory of diffraction wedge corrections and uniform theory of diffraction UTD rays are used to account for additional phenomenology due to truncation of PO currents at sharp discontinuities. Finally, HFSS SBR Plus also corrects the PO current truncation at shadow boundaries by including creeping wave physics. Therefore, using GO, PO, UTD, PTD, and creeping waves, full physics-based synthetic radar returns can be obtained. In this case, we're demonstrating how HFSS SBR Plus can be used to create a full-scale radar scene. Now, I must note that all the actors that we see in this scene are the physical size that we would observe in real life, and this scene is simulated at 77 gigahertz. HFSS SBR Plus allows us to be able to create waveforms such as this FMCW waveform that can be used for typical radar simulation. Here, we are observing how HFSS SBR Plus can be used in conjunction with the VRX driving simulator to model the driving performance inside in a realistic scene. What we're seeing here is that the ego vehicle, that is the red vehicle, can sense the environment around it using a full physics approach. We're seeing how there's some radar returns that are distributed over the entire scene, and this is different from what you would observe if you're not using a full physics approach. Of even greater interest is notice how the pedestrian passing over the vehicle is showing some micro-Doppler effects. We can also see these micro-Doppler effects from other vehicles that are coming towards this ego vehicle because they have that scintillation of the radar returns. To further investigate this micro-Doppler, let's look at why micro-Doppler is important. As vehicles are migrating from level 0 to level 5 autonomy, radar will need to detect and classify targets. Now, using this micro-Doppler response of targets, we can obtain more information about the micro-motion characteristics of a target and not just the velocity of the bulk platform. Now, full physics simulation can capture this distributed nature of this target and the micro-motion induced Doppler shifts. In the first case, we have the bulk motion being attributed to the torso, and the micro-Doppler is being introduced by the swinging arms and legs. In the second case, the bulk motion can be attributed to the vehicle, and the micro-Doppler is being introduced by the wheels. Here are two cases where we can use HFSS SBR Plus to obtain the evolution of the range Doppler maps of these targets when the human is walking with swinging limbs and therefore exhibiting the natural micro-Doppler motion that we would like for that target classification. And in the second case, we just have this drifting human, which is a non-physical situation. However, HFSS SBR Plus allows us to be able to capture this physics of Micro-Doppler. Furthermore, we can even post-process these results and get the spectrogram. And looking at these two spectrograms, we see how by conducting spectrogram analysis, a radar sensor can actually detect the presence of a pedestrian. We can do the exact same case for a car, where we can see that the presence of Micro-Doppler induced by the wheels leads to a spread in the Doppler waterfall plot that we are observing here. All these results were obtained by conducting post-processing of the full physics synthetic radar returns that we observe from HFSS SBR+. HFSS SBR+ can also be used to investigate the performance of radar scenes in corner cases. A very popular corner case that can be debilitating for radar sensors is guardrails. Guardrails have a very large radar cross-section that can serve to blind and possibly even confuse a radar sensor. How do they do this? Well, guardrails provide very strong radar returns to the ego vehicle that can mask the presence of crucial targets. Furthermore, they present themselves as ghost targets that can further confuse the radar sensor. Here we're seeing how this vehicle and a pedestrian and a cyclist can somewhat be hidden completely by the presence of these guardrails. And so because of this, by using HFSS SBR+, we can investigate and look at full dynamic driving scenarios and see what the radar sensor will be seeing. And in this case, we can observe how the guardrails are presenting themselves as this cloud of strong radar returns that hide the presence of crucial targets while also introducing ghost targets. HFSS SBR+ can also be used to design even more complex radar sensors, such as the ones used for MIMO, for angle of arrival. In high density areas where we have a lot of pedestrians and vehicles, fully autonomous vehicles will need to be able to separate targets in angle. This means that in addition to having high range resolution, they will also need to have high angular resolution. To do this, we use MIMO antennas, since they're an efficient use of the hardware, because because a single input and multiple output sensor is not an efficient way to use the filters, mixers, and analog to digital converters inside the radar sensors. So using HFSS SBR+, we can create arbitrary arrangements of transmit and receive channels to realize virtual antenna arrays that we can use to test for performance in full-scale traffic scenes. In this case, we are placing this sensor on the ego vehicle with an arbitrary arrangement of antennas in a way that we would like to test it. In the next slide, I will show how we can obtain angle versus range results for 8 transmitters and 16 receivers. What we did in this case is, using HFSS SBR+, we mounted 8 transmitters and 16 receivers to realize 128 channels. The synthetic radar returns from this simulation were then post-processed to obtain the angle versus range representation of this scene. By simply looking at the scene and these results that we're seeing, along with the distributed returns of these targets, we observe how HFSS SBR+ can be used to simulate such complex traffic scenes for multiple channels. We can also use HFSS SBR+ to pick an arbitrary number of channels in order for us to evaluate how well a particular number of channels can be, in order for us to realize the performance in terms of azimuthal resolution or elevation resolution for different applications. Here we're showing how the 128 channel gives a much better angular resolution and will most likely be the best approach to use for high density regions where we have targets much closer in angle. Finally, HFSS SBR+ can be used for vehicle-to-everything systems. The approach that we will use in this case follows very closely to what we were doing before in automotive radar. For vehicle-to-everything, We use HFSS to design the antennas. We use HFSS FEM as well to evaluate the impact of radome and any closed electronics that may be near the V2X antennas. Then using HFSS SBR Plus and IE in hybrid simulations, we can go the next step of evaluating how these large electrical platforms can affect the radiation characteristics of the antenna. Now, finally, HFSS SBR Plus can be used to determine the antenna-to-antenna coupling for two vehicles or a vehicle and the surrounding infrastructure. In the bottom right figure, we demonstrate how the same antenna, such as a dipole, can have two distinctly different radiation characteristics that mainly depend on the nature of the platform where they are mounted. On top of a small vehicle, the antenna retains most of its omnidirectional pattern, while on a truck, this antenna becomes more directional. Now, the benefits of vehicle-to-everything technology are well known. They include improving road safety. In fact, NHTSA estimates that safety applications enabled by V2V and V2I could eliminate or mitigate the severity of up to 80% of non-impaired crashes. V2X will improve traffic flow efficiency with energy savings, and finally improve the various operational aspects of fully autonomous vehicles. Using Ansys HFSS SBR+, we can even investigate the impact of dynamic obstacles on a V2V communication link quality. Here we're seeing how the introduction of this vehicle leads to a degradation in the communication link between these two vehicles and causing an outage while this truck is between them. We can even compare the accuracy of HFSS SBR+ for these electrically large problems. We can compare these results with measurements. Here, we replicated a simulation. We replicated a measurement that was done for two vehicles approaching and departing from each other to see if HFSS could predict the received signal strength. What we see is HFSS not only predicts the received signal strength, but it can also show and predict the points where we observe the characteristic drop in the signal that results from multipath propagation. So what we see here is that HFSS SBR+ can accurately predict the received power and the spatial locations of multipath induced nulls. Now, in summary, what have we talked about today? Well, we have discussed how Ansys offers a comprehensive solution for ADAS applications. We have demonstrated how multiple solver technologies available in AEDT enable the efficient, fast, and accurate solutions to be applied to electrically large and complex electromagnetic problems. We have shown how Ansys Electronics desktop AEDT can be used to design antennas with HFSS FEM and to evaluate the impact of antenna platforms on the performance of those antennas. Ansys Electronics Desktop can be used to accurately predict the coupled power between two antennas for V2X applications. Finally, AEDT can be used to accurately capture the scatter fields in a full-scale traffic scene at 77 GHz for automotive radar applications. Micro-Doppler, corner cases, and MIMO AOA were some of these applications. Thank you for your time.